Good morning. In this lecture, we start looking at the processing of large continuous networks and the various tools that we have to assist you in setting this type of processing up. Basically, we're going to look at the issue of how you go about generating large gamut solutions where you have more than 50 sites or more than 100 sites. And this could be regional networks where you want all of the sites to be processed in that particular region, or you may be looking at a solution in which you want to have global networks and you have a large list of sites to choose from and you want to automatically choose a certain number of sites as you go through. The global network processing is something that we do for the IGS each week, and this is more the type of processing that most users would do associated with their own analyses. The gauge noda network, for example, was processed with these types of techniques. So we're going to look at some of the strategies for doing large network processing in GlobeK, and we're going to look at what we often call prototyping tools. The idea here is that for these large solutions, the amount of CPU time needed can be very extensive. And you would like, when you run the GlobeK solution, that you only have to do it once or twice. And so you can test beforehand whether the solution is likely to have issues or not. And then, so the idea is to run GlobeK to set up time series files using this program called tscon, which we'll come back to later. It's TS for converting, and glist to let you see exactly what your renames, etc., will do in the solution. And you can use the program tsfit to fit the time series and assess the quality of the results that you have. So these strategies for large network processing. As I mentioned earlier, gamut is limited to 99 stations. It's, in the current version of the software, impossible to exceed this number. And it's also not obvious that you want to go too much larger than this number, primarily because the speed at which your run happens tends to go as the cube of the number of sites that you are processing. And the reason it's the cube has to do with that the number of sites sets the number of parameters, particularly the ambiguity parameters that are needed in the gamut processing, and the large rate determining step in the processing is the inversion of the normal equations and then ambiguity resolution. And the inversion of a matrix essentially goes as the cube of the size of that matrix. And so that's why we typically don't process networks larger than about 50 or 60 stations. And 99, as I said, is the maximum number. The earlier examples we were looking at for the GNSS processing test used 98 stations, and that worked out quite well. If we wanted to go further than that, we would have needed to subdivide the network. Now, the process of actually dividing the network, you can do that in SH gamut calls, and there is an option called net extent. And the standard way you do this is that you have multiple day directories, and you use the net extent term to differentiate between the different networks. So for a given day of year, you may have N1, N2, etc. If you're going for larger networks, you can make this little string as long as you like. So you run each subnetwork separately in gamut, and we'll talk about how you set those subnetworks up, and then you combine them together in GlobeK, processing each day of the week, each day of the data. You can run h2global to generate the binary H files, GLX files for each of the subnets. And then if you wish to, if you want to have a basic idea, you can use shglred to combine them together. This minus option basically tells it to go and look for ASCII H files to be converted, and then the minus net option to select the different types. In general, we find that shglred, because of the flexibility, the types of things that people want to do, is a starting point, but nearly, I think, everybody who does this earnestly develops their own shell script, specifically aimed at how they've decided to set up their network processing. For example, our IGS processing, we don't use shglred at all. simply because the way we structure our networks, particularly for the GNSS processing components, isn't really compatible with the way that SHG or RED works. There's also an issue you should be very careful of, is that if you're processing in baseline mode, then you have to use the -A option in H2Global when you want to combine networks together. If you don't do that, each of your networks is essentially free to rotate independently of each other. And then finally, as I said, we use these prototyping tools, the TS-Con, TS-Sum, and TS-Fit, can be used to identify where there's breaks and outliers in your time series before running this very large, time-consuming velocity field. The largest fields that we have tended to run have been associated with the gauge NODA network, where the number of stations is of order about 2,000 over the period of over a decade that the network has been available. We've processed from 1996 through until whatever the current date is. And those runs completely take about a week or so to actually complete. And we test them beforehand, again, using these TS-Con programs, etc. So when you want to do large regional networks, so this is a case where you have 400 or 500 stations that you want to process, and you want to process every one of those stations. And so you're going to subnetwork your stations. And the program you use to do that is called NetCell. And it has various options. And then when you look at the full help for it, it has more options than that are listed here. There's a little bit of an explanation of how to do it. Anyway, so the basic thing you tell NetCell is a list of RINEX files that you'll generate with an ls-s. And the reason you put the -s in is this is the size of the RINEX file. There's going to be some internal checking and some codes you can set, or options you can set, that limit the size of the RINEX files that get used in the solution. So discard ones which are very small, for example. You also give it a GlobeK velocity file, which you extract from either a TS-Fit run or from a GlobeK run, or it can be extracted in multiple ways. The idea here is that you want to have the latitude and the longitude and the site name of the site. We're going to use that latitude and longitude because we want to look at the geometry that these networks will go. And then you have an option of the number of sites you want on each network. This number will actually get adjusted depending on how many sites are actually there. So it will choose a number where you have approximately the same number of stations in every network. And then you tell it how many tie sites to go between the networks. And that number must be greater than 0. And the number you choose here, again, depends a little on the network sizes that you have. When you're dealing with just a couple of hundred stations, you might use 1 or 2, maybe 3 sites to tie each network together. But if you're dealing with very, very large networks, such as the NODA network, for example, you may actually only be able to have 1 tie site between each of the networks. But that should be perfectly adequate. It's because you're going to control the earth orientation, the translation, and these networks are combined. Tying with a single site between each of the networks is perfectly adequate. So what's going to happen is in this program, when you generate the networks, it generates each network with completely independent numbers of stations, and then it generates a tying network that ties all of those networks together. And this tying network is the one that you select the number of sites from. So if you have 20 subnetworks, for example, if you choose 2 tie sites per network, then you end up with a network of about 40 stations at the end. If, on the other hand, you have 100 subnetworks, then we would actually have an issue because you'd have only 99 sites that could actually be in that final tie network as you go together. We've never reached that magnitude of network to be processed at any one time. So you also specify the station.info file, and this is mainly, again, for automatic processing. This just ensures that the RINEX files that you have, that there is a station.info entry associated with them, so that when the sites.default file is generated, it can tell the software whether it needs to actually generate that station.info itself. And then finally, there's just the code that you use to generate the names of the networks. And For these large regional networks, it's a 2-character code, and then the network number itself is put out as a 2-digit number as you go across. And finally, in the most recent versions, 5 years ago now, there is another option in here, which is actually to subnet Globe K networks. And so this is going to use the random walk information that's telling you the quality of the data that is coming from each of the sites in your network, and it's going to divide the network into subnetworks for Globe K to use, and you're going to use the Globe K command options to be able to use site command in Globe K to be able to actually specify those networks. Again, this is the strategy that we need to use for the very large NODA network processing. So the way Network Cell works, it outputs to the screen and generates essentially what you can extract out to be the sites.default file. Again, this is using the method that things of interest have a blank in the first character, but it basically is just telling you the information about how many sites you have in the network, how many total sites there are. This one is 1,500 stations, 1,500 stations. The number of the stations that are available in the Rhinex on that particular day is 1,234. It gives you information about how big your network is, and then it's telling you that this final network will have 39 sites in each of the 32 networks, and then with 25 sites in one of the networks left over. And then it gives you the list of information and information about how the network is actually being created. So the way this works with the output and the ties is that this algorithm starts by looking at the highest density network in your area, and then chooses the first group of stations to be centered around that high density region. And then it removes those stations from the list of stations, chooses the next highest density region. So when you're doing something like the NODA network, for example, this particular algorithm typically starts in Southern California, essentially works its way along the San Andreas Fault, and then slowly builds up the final networks, which are the pieces left over the networks. And as I said, there is a final network that gets added, which is the Centroid Network. What this does is it takes each one of your networks and it chooses the site which is near the center of the network. And then if you have more than one tie site per network, then it chooses the next one, which is sort of a quarter of the way out through from the edge of the network together. So again, typically, provided the data quality is high, the actual specific locations of these network sites is typically not particularly critical. And again, stressing that when you run H2Global with the baseline mode, you have to use the -A option there. So the outputs of these site.defaults files, which tagged by year and day, and those can then generally be automatically used in SH gamut processing. The experiment code and the net extent are normally set to something like NEXX, where XX is the network number. And the shell's script for SH gamut can then be called and can be passed, typically when we're doing these large networks, into this portable batch parallel processing system for large clusters. This is the one that we use for the cluster at MIT, which is out at Holyoke. And basically, it allows each one of those networks to be processed in parallel. There are some other subtleties which in the tutorial sessions we will talk about, having to do with generating G files when you're running these parallel runs. So again, the only thing you worry about in parallel runs, the biggest thing you worry about is files potentially overwriting each other as the parallel run happens. So this is the basic technique you use when you have a large regional network and you want to be able to divide it into subnetworks and process all of those data. The other process you often sometimes will be interested in is global network selection. And again, depending on the type of analysis you're doing, this is where you have a large number of stations from around the world, and you want to basically build networks that each one of the individual networks covers the globe as uniformly as possible. We actually have a program called Global Cell Level that does this, but this particular operation is sufficiently complicated that we typically use this SH network cell shell script to build up the pieces that Global Cell needs. And again, it does exactly the same thing in that it makes sites.defaults year.day files, and then it will automatically can be used again in SH Gamut to process each of those data under the experiment key for each one of those networks. So this shell script uses FTP lists of the available data on a given day, and so this builds up that global network. So the standard approach here is to FTP a list of available files and their sizes from the various archives around the world, CDDIS, SOPAC, IGN. There's a list of about a half a dozen that we typically use. It's interesting, if you explore the whole world of available data, you potentially are looking at up to 10,000 stations being available for processing right now to go. So we build a core list of stations to start with. And so you basically tell it how many networks you want to create and how many stations should be in each of those networks. And then the networks are seeded with just a few stations from each of those regions. And the only thing you have to be careful of is to choose stations which are long-running, regular using stations, so that on any given day that you have at least one of those stations from the core network being available. So in the way we build we'll talk a little bit more about that in the next slide. The way we build each of the networks is to share a number of tie sites. So every network shares one tie site with every other network. The consequence is that no station is ever used more than twice in the way this algorithm is constructed. And then there's some interesting aspects if you want to look at how we form double differences and this uniqueness of double differences. When you use a full variance covariance matrix, you can show that it's close to rigorous almost in the way these one single sites, even though they're used twice, because of the way the double differences tend to be formed, you're not really necessarily overusing data when you do this. So that reference site list that we talk about is made up now of a set, basically a RefNet line, and then this is the name that you wish to give the network. So again, the networks here tend to be, as you wish to name them, as opposed to numerically. We generally do a numeric 6-character, numeric character here. And then this is the group of stations that you want to use. It's important they're separated by vertical lines, no spaces in here. And the idea is that the network is seeded initially with whatever of these stations is available, and the rest of the network is built out from that particular location. Again, normally when you're doing these large global network solutions, this is what we would use for doing the IGS orbits, etc. And so most users don't tend to use this particular aspect unless they're really interested in understanding global processing going on. And as I said, if you wish to go out and start processing those 10,000 potential stations that are available, this is one of the techniques that you could use to do that. And if you have enough CPU and cores available on a parallel machine, that would be a successful processing technique. However, when you're doing those very large solutions, it becomes critical that you have a good sense of whether the solution is going to work before you start running the Globe K-run. And again, as you have large 1,000-station networks, it's not uncommon to have each one of the steps in the Kalman filter to take maybe a minute or so as you bring in data. And as you bring in many, many data points, many time intervals, that time can really stretch out to a very long run time, 24 hours, 48 hours. So you want to make sure that it's going to succeed as you go. And again, inside Globe K, we have these options such as that the maximum chi-squared increment. So if something is wrong in one of your H files and the maximum chi-squared increment is too big, it will throw it out. So it should not corrupt the solution. Similarly, if you have a bad station coordinate, typically more than a meter or so error in its a priori coordinate, then it will also throw that out. What you're trying to avoid with the prototyping tools is that you throw out more things than you intend to throw out in the automatic Globe K run, because it will still take it a long time to run. So ideally, when you run globe K, you would like those automatic chi-squared increments and those automatic outlier detection algorithms not to be needed, because you've taken into account already all of the potential discontinuities, large earthquakes, etc., and bad station identifications that might be in your data set as you go. So we have a couple of programs to do these types of prototyping things. And the big one is a program called TS-Con. It normally means TS-Convert, and it has two roles that we use it for. One is that it actually converts a variety of different data file formats into the PBO-POS format that was developed for the Plate Boundary Observatory. This allows new reference frame, so you can do the conversion of different groups' works. For example, the University of Nevada's TXYZ2 format files can be read with this program. We can read various formats from the measures program, various ones from the JPL program as well. So you can convert the file, but also it allows you to redefine the reference frame realization as you go. And it uses techniques very similar to geolog. In fact, its command file for these are the same style of commands as used in geolog to do this. And you can then specify the stabilization just to test to see how well your list of stabilization sites will work as you go through. So TS-Con has these two roles of converting formats and also being able to realize a different reference frame. So if you had UNR solutions, which are in the IGS 14 frame, for example, with their latest release, and you wanted to convert them to North America fixed reference frame, you could choose a set of stations that define the North American reference frame, and then take those time series, a whole group of stations, and then be able to rotate and translate those onto your North America reference frame realization and generate time series that are then in North American fixed reference frame. So to sort of test whether your results look any good or not, then we have the TS-Fit program. And again, the idea here is the TS-Fit uses many things that come from the globe K processing itself. In particular, TS-Fit allows you to read multiple globe K earthquake files so that it knows about the discontinuities in earthquakes that you're able to put into that processing when you run through globe K. TS-Fit also outputs globe K files, such as the a priori coordinate file. And this is the way we tend to generate a priori coordinate files now. So we have a set of EQ files, we run the time series, and we can then generate APR coordinate files with all of the extended entries that are needed to represent the potentially periodic signals, but also the earthquakes and post-seismic deformation as we go through. When you run TS-Fit, it also uses what we often refer to as the realistic sigma option, or the FOGMEX algorithm that Mike talked about in the time series analysis part. So this is an attempt to obtain information about the correlated noise characteristics of your data. And then SHGenStats can use the statistics that come from the fitting, and that allows you to generate the random walk process noise models that you need for the globe K run as you go through. TS-Fit is both a weighted least squares program and a Kalman filter. And later on, when we're looking at some results, we'll look at the issue of how those two things compare to each other. So TS-Fit can use the process noise models that you would be using in globe K, and again, to give you a measure of what the uncertainties will look like as you go through. And finally, the program TS-Sum is actually the one we use to extract time series from typically the geolog outputs from globe K or from GeoRed as you go through. The nice thing about TS-Sum compared to many of our older tools that we no longer use is that this program will append to existing time series. So if you are doing regular processing, then you can just simply append the new results onto an existing time series files. If you reprocess something and rerun it with something that's being reprocessed, it will replace the values that are there. And there's various other options as to how to treat those a priori time series files that already exist. So again, fairly extensive help on TS-Sum to look at that. And again, these can be automatically generated from GlobeK outputs. So the basic idea of the prototyping type concepts is to generate your earthquake file and your list of stabilization sites that are going to be used in your GlobeK runs, and then use tsfit and tscon to see how well that particular choice is going to work based on your time series files. The program glist, which is the one which tells you the stations and satellites as well that are in your binary H files, also reads EQ files, and so it can generate the full list of stations that you're going to use, and it can also read the use site type commands. So it will tell you precisely what stations are going to be in your GlobeK solution. One of the things we've noticed with particularly large campaign style processing and complicated use of earthquakes and use sites to keep a number of sites down is sometimes sites get lost and people don't know why they don't have an output for a particular station. And these tools in glist allow you to get a sense of what GlobeK is going to see when it does its running as you go through. There are also options in GlobeK, if you look at the output options, that let you get the parameter list that GlobeK is going to use when it's doing a large solution. And that parameter list is useful. It's generated right at the very beginning. And so you can look at that and make sure that the stations that you think are going to be estimated and the velocities you think are going to be estimated are actually in that list. These days, glist also includes model summaries, just to see, it'll tell you essentially whether the models that have been used in the gamut processing are potentially inconsistent as you go across. So tscon and tsfit can read the standard GlobeK earthquake files, and as I said, the tsfit a priori coordinates include the extended entries that go out. So the nice thing about these programs, or tsfit and tscon, is since they're dealing with essentially a diagonal covariance matrix at each day, there is no correlations between the stations in here. They can run much, much faster than the GlobeK run, which is essentially propagating full variance covariance matrix across between all of your states as you go across. And so it does assume that you start with a set of coordinate positions which are well stabilized. Although again, theoretically, you could start from coordinates that have never been through the origin definition system. The only complication there is that all of the uncertainties on the sites would all be pretty much the same and all be large. And so the advantage of the stabilization is that you have appropriate relative standard deviations between the individual sites when you are doing this. So the basic strategy one uses on this type of processing is to first run glred to generate time series. And again, you might just do this, and a very common thing to do is just use the standard IGS 2014 files that we supply and the standard stabilization lists to go through to generate those time series. And from those time series is where you're going to start doing your analysis to refine the way that you are doing this approach as you go through. And there is this, what we sometimes refer to as a catch-22 in this, is that to generate good time series, you do need to know which stations are well behaved and appropriate as reference frame stations. And you don't know that until after you've actually generated the time series. But again, most of the time, the sites that are in the IGS 2014 stabilization list and the internal editing that happens in glred in terms of frame stabilization pretty much ensures that nearly always this works out quite well. You don't need to iterate in the sense of getting rid of bad reference frame stations at the beginning. So once you have that initial set of time series, then you can use tscon to generate new time series in different frame stabilizations as you wish. So you may have done this in the standard no net rotation reference frame, but then tscon you're going to be able to use now with more stations potentially using your own regional local stations and generate a frame in a frame which is more appropriate to the problem that you are trying to study. You carry out the analyses of these time series with tsfit, and then there's also a shell script sh plot pos that allows you to plot the time series and the residuals from tsfit, etc. And you can also generate a new a priori coordinate model and any additional parameters such as seasonal terms that you want, earthquake post-seismic deformations, jumps in time series, etc., can all be put into this field. It is important when running GlobeK is the apiary coordinate file that you're using in GlobeK. You should be careful and make sure it is as accurate as it can be, because there are a number of things in GlobeK where what you're actually adjusting, what you're looking at is the difference between what your apiary value is and what your estimate was. And if your apiary value is bad because you've somehow mixed together, say, site coordinates from a no net rotation reference frame with site coordinates from a North American reference frame, and they could well be tens of centimeters difference because of the difference in rotation between those frames. Those sorts of bad mixes in the apiary coordinate file can have impacts in GlobeK that can be subtle, again, because GlobeK is really working with the difference between your apiary and what your actual estimate is. So if your apiary is not good, it can corrupt the results that come out of GlobeK. So programs like TS-FIT are a nice, convenient way to ensure that you have a consistent apiary coordinate file, and we strongly recommend that you do that type of approach when doing large solutions. So continuing on in the way we basically process those time series fits that you have generated by TS-FIT, you can use judge quality. The summary file that comes out of TS-FIT can be used in SHGenStats with -TS option. And you can also remove outliers in TS-FIT using a N standard deviation condition. Generally, you want to set this to be maybe 3 or 4 or 5. If you make it too small, it'll actually throw out all of your data because it iteratively applies this condition. And this, the outlier rejection points are written out as in standard EQ format files with XPS lines or XCL lines that get used, XPS typically. So you can also use those APR files that you generated from TS-FIT. They can be also used in TS-CON to again, refine the reference frame realization as you go through. So again, these types of runs, they take a few minutes, typically even for very, very large networks. So you can afford to play around and try different scenarios here to get a good sense of how things work. Later on this lecture, we will look at exactly how much difference there is depending on how you actually approach these as you go. So basically, the idea is to generate the best reference frame solution you can as you go through. So once you've finished all of the TS-CON, TS-FIT processing, you should have available an earthquake file that contains all the earthquakes and renames. And remember, things like earthquake files, you can have multiple different files that can be all read into GlobeK. At some level, there is some ultimate maximum limit as to the number of edits, etc., that you can have. But because we use all of this to do the gauge node processing, that tends to be a really large number. And most users don't come close to the large numbers of extended number of sites that we have to process to do that. And again, you finally get your reference frame sites from SHGenStats. And again, there are, for very large networks, there's options in here that will balance your network across the whole region. So you're not putting all of the high quality stations in one region of your network. For example, if you generated high quality reference frame stations based purely on the level of correlated noise in the time series, you'd find you'd get dominated by the Mojave Desert in California, because those stations in that region tend to have very, very low levels of correlated noise. But then your other stations in other parts of North America would not have as much weight in terms of the reference frame realization. So these options allow you to basically geographically have hierarchical lists that can be used. So then hopefully, if this is all done very carefully, then your final GlobeK and GeoRed runs will go through with no major problems. And again, this is the technique that we tend to use when we're doing the large annual velocity solutions for the gauge node network, which, as I said, have well over 32,000 parameters in the state vectors. We had to modify GlobeK to handle larger than integer star 4 numbers of parameter in the covariance matrices, etc. Okay, so TS-FIT, this is again one of these programs which has many characteristics to it and commands in it which match those in GlobeK so that you can use the GlobeK style to essentially run the fits on your time series as you go. In particular, it takes the types of formats that we have, and as I said, it allows you to incrementally update your time series, and then you can also output API coordinate files, and then this report edits option lets you put out the edits that are applied to that data in an EQ file format. So one of the big differences, many of the users who have been around Gamut and GlobeK for a long time are used to using the program ENSUM and multibase. We don't recommend these at all anymore. In fact, none of our modern tools will work with the outputs of these programs any longer. And the problem with these programs, in many respects, is that you need to regenerate the time series from your original org files every time you add a new data point to it. The program TSSum incrementally updates these files, so it becomes a much easier way to do it. It's easier to replace a bad processing. You can go back and just do a few days of data and then update all of the time series with the replacements on those two things. So the tsfit is again command line driven. It takes tsfit, takes a command file name, a summary file, which typically we end in .summary, and then a list of files to be processed, POS files to be processed, or a file that contains the list of files to be processed. There potentially with C shell, there can be limits on how long these lists of strings can become. So if you have many, many files with a long path leading to the file name, it might actually overflow some C shell limits, and that's when you'd have to specify a file containing the names. Generally, we haven't hit that problem very much in recent years. So the main commands in tsfit that you most likely use is, again, the earthquake file. It gives you the standard earthquake file, and it can be used multiple times. The output APR file tells it the name of the output file that you want to generate, which will have the a priori coordinates, and most importantly, the extended entries for periodic terms with all of the appropriate names for the stations in the extended terms. Report edits gives you an earthquake file. It contains XPS lines. And then real sigma is the command you use to invoke the FogMex algorithm to come up with estimates of the correlated noise within your system. You can have periodic terms where you just give it the period in days. And again, this will estimate sine and cosine terms with that period. And then you can issue this command as many times as you want. There is an output, which is the site-dependent information for each one of the individual sites has its own file generated with this. It typically, by default, starts with the string ts underscore, and then the name of the site, name of the POS file, etc. would follow after that. In many cases, these files you don't want to generate if you don't really need the details. So you can actually use the command, say none, all uppercase, for this det root term, and that will stop those terms being output. You can generate a standard GlobeK velocity file, which you can then use in shplot POS for plot.vel, for example, or in VelView. And then, as I said, there's this n sigma sigma limit, which lets you run as you go through, run error checking and deleting of data as the time series is processed. Again, you have to be a bit careful sometimes with very large systematic time series, because this type of algorithm can extensively throw out large amounts of data if you're not careful. You can use wildcards in the tsfit commands to replace things. Typically, the base for the wildcard is the name of the summary file, etc. And we have not yet implemented the time arguments in tsfit that we have in GlobeK. Partly the reason is that tsfit is not run quite in the same batch-oriented mode that we tend to run GlobeK in. So right now you have Globe wildcards that will be based on the name of the summary file. So some of the others are the match standard deviation lets you limit what the uncertainty of the data points is you're going to use. Time range can be quite useful, and it's basically the start time. The end date is optional. If you don't put the end date in, it will only process, it'll process up to your end of your data. And it's given as year, month, day, hour, and minute. And it's important to note that the hour and the minute here has to be the midpoint time of your processing, which is typically 1,200 hours for just about everything we do. You can also output earthquake files and the amount of post-seismic deformation at a particular number of days after the earthquake. And these files are all consistent with the format of being able to plot them in shplotvel and VelView as well. So this is particularly for post-seismic deformations and logs. And you can also estimate exponential coefficients in this. Now, I must admit, for handling post-seismic deformations in GlobeK at the moment, our standard approach is to estimate the post-seismic terms using TS-FIT and then use those as the a priori values that are used in the GlobeK processing. That's a much more straightforward way of handling the process and the process noise on some of these post-seismic terms. Again, and when you output at a specific output time period after an earthquake, for example, it actually does rigorously compute all of the correlations as it sums the logs and the exponential terms to tell you as good a estimate of the uncertainty of that change in position after that post-seismic deformation. And again, you have exponentials and log terms that are available. In both the log and the exponential, you have to specify the time constant. We don't put in yet the nonlinear process of trying to estimate time constants. We have tried that in the past. It tends to be somewhat unstable. And so right now for operational processing, we don't do it at all. Okay, so TS-Con is the other program we've been talking about. And this is the one which converts time series. There's various formats. It'll do it from the NASA Reasons Program time series, which these days are available at CDDIS, Jet Propulsion, or various scripts formats. There was a Southern California earthquake, sent us comma-separated file that it could use, and then the UNR formats can be converted over as well. The UNR time series, for the older ones, there are some issues which you see in the help described about the east coordinates of the sites, and that is something which is no longer necessary with their IGS-14 processing. But again, one of the things you learn with scale here is both UNR and JPL and the Reason program all estimate scale changes when they're estimating that time series. For the UNR and JPL solutions, it's possible to get the estimates of what those scales are, and we have some shell scripts that you have to actually read individual files from. So again, be aware that when you're dealing with those files, they have scale estimates removed from them, and they could well differ from the results that you see where you're not estimating scale changes as you go through. And again, these TS-Con basically assumes that you are dealing with 24 hours of interval of data centered on 1,200 hours. You can also have no command file when you run TS-Con. You just put in a pair of single quotes, what we often call a space holder. And if you do that, then the program will simply convert the file format. It just converts the format. It does not try to make a new realization of the reference frame when it does it. So again, the TS-Con run string is you give it the name of a directory where you want the output files to go, the new POS files. This product ID, which when you look at TS-Sum, is this string that typically contains information about the processing center. Something about the age of the orbit is the historic way that it was formed, and then the reference frame in which the results are being given. And again, this is a fairly flexible piece of information. We use it in various ways, as you'll see when we look at some time series later on. And the command file, as I said, is a standard command file generated for TS-Con, or it can be just a single pair of quotes as a placeholder. And then the list of the files, or the files, a file which contains the list, the same way as we saw with TS-FIT before. And again, so some of the major commands that you deal with here, again, is the earthquake file, APR file, stab site, the position origin that you want to use, number of iterations that are going to be used, the stabilization minimums associated with essentially the minimums height sigma that a site has to have for it to be used in the stabilization. Again, there's condition on the height variance. This one only takes 2 arguments because there's no velocity term in TSCon. It's just doing one day at a time. And again, time range in the same way as we had it for the TS switch program again. And all of these commands are meant to be geolog equivalents. But again, because they're dealing with time series, there are small differences in the way things work. So as we look at this, how does this whole system sort of work out? Well, this is an example. It's from the PBO NOTA field. This is in the central part of the United States. And the velocity scale down here is a 5 millimeter vector. And then what you're actually seeing in 2 different colors are the velocity estimates in a North America fixed reference frame that are coming from the globe case solution, full rigorous globe case solution, and the time series fit using TS fit. And when we did this, we'd actually subnetted the globe case solution down, and we only used 1 day per week. That's another time saver you can have when you have large continuous networks. When you take into account process noise, you really don't need to use 7 days a week of data. We have found 1 day a week works perfectly well. There's very little difference in either the answers or the uncertainties with correlated noise included, whether you decimate down to a factor of 7 in times of your processing. And with the decimation of a factor of 7, it runs 7 times faster, which makes it very, very useful. So the same process noise model was used in each of these, and we'll look a little bit more detailed at some of the actual numerical results that come out here. But this match is very good, and what we're going to find is the deviations here are typically about half the size of the standard deviation of the individual values that we are dealing with. So again, if we do a comparison over here, on the side over here is actually the detailed statistics between those 2 fields. So this was done in Bellevue, and what we did was we aligned the 2 fields. So we have the TS fit Kalman filter solution with the globe K Kalman filter solution. And what has been done is we've estimated just a simple translation of the field at delta north, delta nu, delta east. So a translation of this field. And those translation numbers are of order about 0.1 millimeters per year. And then after that, we have the RMS difference between the 2 fields after we've done that transformation. And as you can see, those numbers are running at less than 0.1 millimeter per year RMS differences in those velocity fields. And then the normalized RMS, which is the square root of chi-squared per degree of freedom, is running at less than 0.5 on these things. In the height, we have a slightly larger, about a 0.6 millimeter per year average height offset between the 2 solutions, and the RMS is around about 0.25 millimeters per year. So one of the things we use as a rough rule of thumb in terms of working out whether something is a significant change when you make a change is that generally if results match within some fraction of the standard deviation with which you determine them, then we think that the match is good. So in this particular case, all of these uncertainties on these velocities are 1/10 of a millimeter per year. And so we're seeing differences of about half that amount. That to us, we consider to be quite a reasonable amount of difference. If these uncertainties were 2 millimeters per year, and we did this type of comparison, we might expect to see millimeter per year differences between them. And again, that would be consistent with having results which are consistent within the uncertainties with which they are determined. And again, this is just the final example of the statistics that were there on that previous page. And as you can see, we do have these very small RMSs. If we look at some of the individual stations that are out here, and in this particular case, we've also now included the differences between the globe K solution and this weighted least squares solution versus the globe K solution and the Kalman filter solution coming out of TS fit. Again, the matches are quite close, and you can see the numeric values down here for a couple of different stations. And you'll notice that the TS fit weighted least squares solution is generating sigmas which are somewhat lower than the Kalman filter fit, and that has to do a bit with the way the FogMex algorithm works. Our preferred method, again in TS fit, is to use the Kalman filter option for the output, because it does take into account the process noise in a random walk fashion, the same way that GlobeK takes it into account. Also, we find that when you estimate offsets in time series with the Kalman filter, particularly when the time series is systematic, that the offset estimate is more close to what you would expect to see by just taking the difference between the few data points before and after that event happened. And again, the final thing you worry about with all of these Kalman filter type approaches, both GlobeK and the Kalman filter in TS-fit, is that it does tend to weight the data more at the beginnings and the ends of your time series as you go through these types of results. And again, there is some, this is not a perfect exact comparison. There are differences in the way the alignment was done precisely between those two as we go through. So gate velocity solutions. So again, we talk about this, the aim of these is typically to combine many years of data together. And with these prototyping tools, hopefully you can make sure that when you run one of these solutions that it runs successfully and you generate the results with the stations that you want to have. So as I said, it's not uncommon for these types of solutions to have over 10,000 elements in their state vectors. And the most recent ones we've been running, that number's been running more like around about 35,000, 36,000 elements in the state vector. That takes a long time to process each increment from the Kalman filter when there is that many elements in the state vector. So when you do this, you need a good a priori coordinate file, and you want to make sure that all of the sites and their velocities are consistent with each other, because again, it's the a priori, the adjustments to the a priori is what GlobeK is going to be working with, not the actual values itself. So if you have a bad a priori coordinate, it can actually impact your results in ways that can be quite subtle, because it's not necessarily that far away. And so our recommendation for large velocity solutions is to generate the time series first, use TS-fit to generate an APR file. And again, you can specify multiple APR files in GlobeK. So one thing to do is to specify the APR file that you generated from your TS-fit one, and then in glorg, say use the IGS 2014 APR file to define the reference frame coordinates that you want to have, just to make sure you stick back to the original IGS reference frame, for example. So you have the a priori coordinate file, which again, for large solutions, you should be very, make sure it's well done. You do not want to really see messages saying that GlobeK could not find an a priori coordinate in your file and instead used its own internal default that it generates based on what was input from the H files. You want to have the earthquake specified so that you know where all the earthquakes, and in particular the discontinuities due to antenna changes, potentially misnamed stations, etc. And this is critical that you get all of this information correct as well. And we spoke earlier about the fact you can take station.info and generate this discontinuities list directly that you need for that. And then you need the noise processors for each of those stations. And again, white noise in these types of time series generates extremely optimistic uncertainties on your velocity estimates and other parameters. So it's critical that you do take into account the level of correlated noise that's in your time series. So as I said, you want to be very careful in this setup, correct a prioris, correct coordinate files, process noise as you go through. And then once you're inside, it can, as I said, take several days for one of these large solutions to work. So some of the strategies that we use, and actually even in the GlobeK part, if we want to be a little bit more cautious, is we may well have 1,000 stations in our network. And the 1,000 stations includes those that have multiple names because of discontinuities. Sometimes it's worth just to use the use site command to limit yourself down to a small number of stations. You might just choose those stations that you plan using as reference frame stations. And then with the small number of stations, the run will happen quickly, and it will give you a good sense as to what the solution's going to look like. And you can in fact use potentially the positions from this smaller run to use as the reference frame realization for the time series analysis to test out various things as you go forward. And you can repeat that step, increasing the number of stations as you go forward in time. As you saw from that comparison between the time series analysis and the globe K run just earlier, we are running a debate ourselves at the moment for these very large networks, whether the better strategy is simply to take the 400 or 500 reference frame stations that we use for the NODA network, do the velocity solution with the 400 to 500 reference frame stations, and then generate the velocities, et cetera, for the other 2,000 or 3,000 stations that we have, just using those reference frame stations. And so generate the velocities for many of the stations purely based on a time series analysis rather than on the globe K analysis. And as we've gone into many, many thousands of stations, that is a strategy that we are thinking about for the NODA processing, for example. So some other strategies you can use when you're doing velocity solutions is pre-combining of daily solutions into weekly and monthly solutions. And this is a common technique often used when you're doing survey mode data processing, where for each one of your surveys that may have taken 2 to 3 or 4 weeks out in the field, you combine all of your survey data together in one monthly solution as you go forward. And then for the continuous data in between when you did surveys, just to have a combination in which everybody is of about the same accuracy and resolution, you use monthly solutions of the continuous stations in between of your surveys as you go forward. So the benefits of doing these pre-combinations, for example, and I would admit definitely if you're doing multiple networks, you clearly want to pre-combine the networks together before you start doing velocity solutions with those networks, just for speed alone. So they run much faster. And again, if you go for a monthly solution, it will be 30 times faster than a solution in which you ran daily as you go through. There's again, one of these more subtle issues having to do with rounding error. And again, with the Kalman filtering, one always has to keep this in the back of your mind that you are starting with a covariance matrix and decrementing it down as you add data together. The fewer decrements you make, the better the numerical stability error. And so it's more than likely from a rounding error point of view, these monthly combined solutions are going to be less prone to rounding error than the solution in which you included the original daily values as you go across. Now, to make these solutions a little more appropriate when doing plotting, we now have what we call a mid-P option, midpoint option. So if you were doing a monthly solution, the default in the Kalman filter and natural in the Kalman filter is that the position estimate refers to the last day of the month. But if you think about the plotting of that, you're actually moving it off by a couple of weeks. And so now in the later versions of globe K for several years now, there's been this midpoint option that would refer your monthly solutions to the middle of the month as you go through. You also have the random walk process noise models, and our tests of doing these types of monthly type solutions has pretty much shown that when you do the monthly combination, the random walk process noise model you use isn't necessarily that critical. It's really when you do the velocity solution combination that the random walk process noise is important. But it would be, it's certainly more rigorous to have the process noise model be consistent between when you run the monthlies and when you run the velocity solutions afterwards. The other type of solution, and these days is again our preferred technique for continuous data, is to actually run decimated solutions. And again, these are good things to test for yourself. Is typically we would use the midday, the Wednesday day of each week, but and the comparisons we have done is to use the Monday data or the Friday data and then compare the results. And what you again find is that for large continuous networks over many years of data, that the estimates you get just using the Monday of the week or the Friday of the week are all very, very similar to each other. And the differences between them tends to be, again, that some fraction of the uncertainty of the results that you have. So summary of large solutions and in general, how you go about subnetting. So NetCell, this is the program that divides up specific lists of stations into subnetworks. So the idea here is when you have a large group of stations and you want to process all of them, you use NetCell. For global solutions where you have a large numbers of stations, but you just want global distribution from a small group of that stations, then it is SHNetCell that uses the global cell program. And again, when you do have large processing, we strongly recommend that you essentially dry run your GlobeCase solutions by using things like TSCon and TSFit to make sure that they always match approximately, that you understand where there's going to be discontinuities and other bad data that might be present. And you can use TSView and LView, which are the MATLAB interactive programs, to assess solutions. And again, all of the processing GMT-based plotting scripts also work with the outputs from these programs. And finally, there's a small program called VELROT, which is velocity rotation. This allows you to actually compare velocity fields as well. Some of the output we did earlier was based on that. And always check the online help that goes with any of these programs, because they do have features that evolve with time. We add new features that are important to what we believe are important to getting high accuracy results from our processing. Thank you.